Okay, this is exam 4 for physics 201. This is only the in-class portion. Remember, there was a take-home portion which was on equilibrium problems. Here, consider a point spinning on a wheel rotating with alpha equal to 0 radians per second squared. Which of these best describes the linear velocity of the point? Well, as it goes around with a constant or a zero angular acceleration, the linear velocity is still going to change because it's always changing direction. So the linear velocity is changing constantly. Now the magnitude doesn't change, it's only the direction of that linear velocity. An object at rest begins to rotate with a constant angular acceleration. So at rest, so theta is equal to 1/2 alpha t squared. If it rotates to an angle theta in a time t, what angle does it rotate in twice that time? It goes through 4 theta because of that quadratic relationship. Figure skater pulls in her arms to decrease her moment of inertia by a factor of 2. As a result, she spins twice as fast. That's because I and omega have to be constant. So if she decreases this by a factor of 2, I have to increase this by a factor of 2. So if that's happened, what has happened to our rotational energy? Where energy is 1/2 I omega squared. I'm decreasing this by a factor of 2. I'm increasing this by a factor of 2, so I get a 4 over here and a half here, so I'm doubling her energy. So her energy is increased by a factor of 2. Solid sphere, hoop, and cylinder all the same mass and radius. Which is the most difficult to spin? Well, a solid sphere, let's see, I think it's 2/5 mr squared. You can look on your equation sheet, just make sure. Hoop is mr squared, so notice no fraction here as a coefficient, and the cylinder is 1/2 mr squared. So the hoop has the bigger moment of inertia, so it's the hardest to spin. Look at these two bars, two equal length and mass bars. Each dashed line shows an axis of rotation. Which of these describe the moments of inertia? All right, well, the biggest moment of inertia is about this axis, because on this axis I have all this mass out at big radii, and then I also have this mass. So A is the biggest, so I can get rid of option D there. B is the next biggest. I still have this mass out at large radii, or not as big a radii, but still out there. So B is the next one, but look, they're all B. And then how do C and D line up? Well, D is going to be the smallest, because if you look down this axis, this mass doesn't contribute at all to the moment of inertia, and this mass only extends out to half the total length. Whereas if I'm looking at C, this mass extends out to the total length L. So about axis C is bigger than D, so A is the right answer. This figure shows wrenches and an applied force, which is represented by the arrow. Rank the torques provided by the wrenches from greatest to least. All right, well, these two have the same torque. I have twice the force here. I have F here, but I have a distance R here and a distance half R here. So the product of these are still going to equal to R times F. So C and D are about equal, so I can just go ahead and say that. B, the torque provided here, is bigger than the torque provided here because I have this angle theta, which makes only a component of this force actually provides a torque, whereas in B, the entire force provides the torque. This figure shows a configuration of object, lens, and image. What kind of lenses produce the image? Okay, well, let's see. First of all, it's an inverted image. Um, it's a lens, so this is a real image. So this lens has produced a real inverted image. The only one that can do that is a convex lens. That's the lens that looks like this. By the way, it's going to be outside the focal point, the object. Concave lenses and convex mirrors. A concave lens looks like this. A convex mirror looks like this, where your object is over here and the mirrored side is here. What type of devices are these? These are both diverging. That means that light rays coming in diverge like this, or here like this. Whoop. For a single lens system, virtual images are always on what side of the object? For a single lens system, my virtual image, my object is here, my image is always on the same side. That's like a magnifying glass. You look in the mirror and see an image of your nose that is bigger than your actual nose. Which of these options correctly give the type of mirror and describe the image? Okay, well, this has to be a concave mirror. A convex mirror can only produce images that are smaller than the object. So it has to be a concave mirror, so it gets rid of all of these. So A is the right answer. It is a virtual image and it is upright. Your object is here, your image is here. This is P, this is Q. It's a virtual upright image. Cylinder has a mass of 3 kilograms, 2 meters, da da da. See, first I want to find what is the net torque. The net torque is equal to the sum of these two torques. First, I just want to figure out which of these are positive and which are negative. So I have a positive torque, or if I look at F1, this is causing clockwise motion, this force 1, so this is a negative torque, and F2 is causing a counterclockwise motion, so it's a positive torque. So to find the net torque, sorry about that, to find the net torque, I say that's going to be, let's see, torque 1 was negative, so it's going to be torque 2 minus torque 1, because torque 1 is clockwise, torque 2 is counterclockwise. Torque 2 is going to be this force times this moment arm, and notice that the angle is 90 degrees between those two, so it's going to be 2 meters times 20 newtons times the sine of 90, but of course that's equal to 1. And then over here I have 2 meters again times 10 newtons times the sine of 30. So that's 40 minus 20 times a half, that's 10, so it's 30 Newton meters is my net torque, and it's counterclockwise. B, I want to know what is the angular acceleration. 2 steps here. I have to know I is 1/2 mr squared. This is I for a cylinder. This is on your equation sheet. That's 1/2. The mass of this is 3 kilograms, or radius of 2 meters. Getting a little sloppy about my sig figs here, but that's 1/2 of 12, or 6 kilogram meters squared. And then if I want to know my alpha, I say alpha is torque over I. That's going to be 30 Newton meters over 6 kilogram meters squared. So it's 5 radians per second squared. It's in the counterclockwise direction. By the way, this was 2 points. This was 4 points because it had 2 parts. And then C, I want to know the angular speed after 3 seconds. This is my angular acceleration. This is my time, 3 seconds. And then D, I want to know the kinetic energy. That's 1/2 I omega squared. That's 1/2 of I, which is 6. That's this value up here, times omega 15. And that gives me 675, or 680 joules. So that's the right answer. This was 2 points. This was 2 points. These are my answers. Okay, a Ferris wheel travels at an angular speed of 0.1 revolutions per second, has a radius of 10 meters. Boy, 50 kilograms, sits on one of the chairs. What is the normal force? Okay, the first thing we need to do is just convert this omega, which is 0.1 revolutions per second, into radians per second. 1 revolution is 2 pi radians. That's going to be what? 0.63, right? 6.28 is 0.63. That's in radians per second. So that's going to be my omega. Get it into SI units. Boy of mass 50 kilograms sits on one of these chairs. So here's my force diagram. My boy sits here. I have a normal force at the top and a weight here. This is at the top. And then we'll do the same for the bottom. I do the sum of the forces equals MA. In this case, my MA, my acceleration, is towards the center of the circle. That's my AC, my centripetal acceleration. I'll put a little C subscript there. Sum of the forces is Fn minus Fw equals mv squared over r. I'm going to write this instead of in terms of V, I'll write it in terms of omega, and I'll go ahead and solve for Fn. So it's going to be Fw plus m omega squared r. What I did there is I just substituted in v equals omega r for v. And since I know omega, you could also just calculate what v is, but this is fine here. So the boy was 50 kilograms times g, which is 10 meters per second squared. That gives me his weight, plus 50. Omega was 0.63. I'm going to square that. And then r, what was r? Is 10 meters. That's the radius of the Ferris wheel. That's going to be 500. Oh, I made a mistake here. This should be a negative value right here because that acceleration is negative. And so here I'm going to have a negative, and here I'll have a negative. All right, it's a very important step. Sorry about that. So it's 50 minus roughly 200. So it's going to be 300 newtons is the normal force at the top. And then at the bottom, it's going to look a little bit differently. At the bottom, I have Fn and Fw still. But now my acceleration is in this direction. So this is a lot like the elevator problem that we worked back in chapter, what, 4, I guess? So now I'm going to say the sum of the forces for the bottom, at the bottom of the Ferris wheel, is Fn minus Fw. So Fn, this is equal to my m omega squared r. That's equal to ma. Fn then is Fw plus m omega squared r. But now I'll keep this as a positive because my acceleration is in the positive y direction at the bottom. So it's going to be 500 plus 200, which is 700 newtons. All right. Let's see, I think I counted this top one as 6 points because you sort of had some extra steps there. And then the bottom, if you got the first one right, the bottom was easy. That's going to be 4 points. Number 13 was just a cross product. Torque is R cross F. That's going to be 1I plus 2J. I get that from the coordinates here and here. Cross with the F3I minus 2K. So I do first, outer, inner, last. I do these two, but I cross I is equal to 0, so I'll just skip that one. Outer, I have negative 2I cross K. Inner, plus 6J cross I. And then last is minus 4J cross K. Okay, now you need to convert these cross products, the unit vector cross products, into their right results. I like to draw my coordinate system to remind me. I, J, K, and then I can use my right-hand rule. I cross K, let's see, I fold into K, it's going to be negative J, so this is plus 2J. J cross I is minus K, so it's minus 6K. And then J cross K is positive I, so it's minus 4I. And that's your torque. The whole thing was just 5 points. You either got it or you didn't. Okay, person stands 4 meters to the left of a spherical mirror. Mirror creates an image that is upright and has a magnification of 1/2. So my magnification is positive 1/2. It's upright, and the magnitude of it is given there. 4 meters to the left of a spherical mirror. That gives me my P, which is positive 4 meters. What type of mirror is this? Well, if it's an upright with a magnification of 1/2, I know this has to be a convex mirror. That's like one of those security mirrors where the mirror side is back here and you stand over here. Now I want to know the focal length of the mirror. So I know M is minus Q over P. 1/2 is minus Q over 4. So that means that Q is equal to, what, negative 2. That jives with what I know for convex mirrors, that they produce virtual images, and this is a virtual image. And then I also need to find the focal length, and it better come out negative because I know convex mirrors have negative focal lengths. It's my lens equation, or my mirror equation, 1 over negative 2, that's Q, plus 1 over 4. See, that's negative 2/4 plus 1/4 is negative 1/4. That's equal to negative 4 meters. That's my focal length for this convex lens. I think that was all. Where is the image located? Well, the image is located to the right of the mirror. The object was located to the left of the mirror. Because this is negative, it's located to the right of the mirror. Two converging lenses, each focal length 20 centimeters, are placed 120 centimeters apart. An object placed 40 centimeters in front of the first lens. Where's the final image, and what is magnification? All right, so let me sketch this out. I have focal lengths here, and then I have another one that's pretty far away, 120 centimeters there and there. This distance is 120. My first object is 40 centimeters right there. Okay, so this is P1 equal to 20, and F1 was equal to, wasn't it? Yeah, 20 centimeters. So now I want to know what Q1 is. I'm sorry, no, I must have a mistake here. Oh no, P1 is not 20, P1 is 40. So that's 1 over 20 minus 1 over 40. So the negative 1, that's 2 over 40 minus 1 over 40, that's 1 over 40. Inverse is 40 centimeters. So this is Q1. And then I can find my M1, magnification, negative Q1 over P1, which is negative 40 over 40, or negative 1. All right, so that's the first part. Now, my image is formed over here. It's inverted, it's same size as the object, and it's 40 centimeters to the right of the lens. That means that this distance is now 80 centimeters. So P2 is positive 80 centimeters, and I want to know Q2. The focal length here was 20. That's equal to 4 over 80 minus 1 over 80. That's 80 over 3 centimeters. This is to the, this is our, actually one of our answers. This is where the image is located. It's 83rd centimeters to the right of the second lens. That's Q2, and it's the final image position. And then I want to find M2 as well. Negative Q2 over P2. It's negative 83rds over, what was P2? It was 80. Negative 1/3. Now to find the total magnification, it's going to be the product M1 and M2. That's negative 1, negative 1/3. That's equal to positive 1/3. That's my total magnification. So those are two answers there. Let's see. And then the last one was just a ray tracing diagram. Draw at least two rays. Okay, so first ray, draw parallel to the axis through the focal point, and then I can draw another ray through the focal point parallel to the axis. This was our rule number 1. Number 2, you didn't have to label them like this, but it produces an image over here. That is a real image, and it's an inverted image. I could do a third ray, just going straight through the center of the lens if I liked, but I only needed 2, and you only need 2 to find out where the image is.